Welcome to the Physics Odyssey channel. Today I'm going to continue my discussion about the physics of roller coasters, and in this video I'm going to talk about what causes the change in direction of a roller coaster as it moves through the tracks, horizontal and lateral G's, zero G curve, negative G curve, conservation of mechanical energy. I should have mentioned this in the first video. I've been focused on vertical and horizontal G's, acceleration, but what causes a horizontal force or horizontal acceleration? So say a roller coaster is moving along the tracks in this direction. So we're looking down from the top. So it's moving this way around a curve. Okay, remember Newton's first law. An object will remain in motion in a straight line unless some external force is exerted upon us. Well, it's changing direction, so there must be a force exerted on the roller coaster car, and that force here is the normal force. So it's the force of the tracks on the roller coaster which causes that change in direction and resulting centrifugal or centripetal acceleration. Roller coaster turns. Unbanked turn, banked turn. It's rare that you'll see a roller coaster make an unbanked turn at a high speed, because such a turn causes very high levels of centrifugal acceleration in this direction. So it'll slam the person riding the car against this side of the car, and it creates a very uncomfortable and possibly dangerous situation. So what you see more often is a bank turn. Why is a bank turn safer and more comfortable for the passenger? That's what I want to get into in this discussion. Okay, so this is a roller coaster car making a bank turn in this direction. We're looking at the rear of the roller coaster car. The banking angle is Greek symbol theta. So why is this a more comfortable turn than a non-bank turn? Well, this equation tells us. This equation describes the horizontal acceleration. So it's acceleration along this axis. And I've created a second coordinate system called the x prime, y prime coordinate system, where the x prime axis is in this direction, the y prime axis is in this direction, perpendicular with the roller coaster seat. Horizontal acceleration consists of gravity, so 9.8 meters per second squared, times the sine of the banking angle. So gravity in this scenario will cause the passenger to slide this way. Centrifugal acceleration along this axis is v squared over r cosine of the banking angle. So centrifugal acceleration will cause acceleration in this direction. So the bank turn has reduced the amount of centrifugal acceleration along this axis because we're multiplying v squared over r times the cosine of the banking angle. And gravity offsets that. So as a result, you'll have less horizontal acceleration. This will provide for a more comfortable ride for the passenger. There's also a component of acceleration in this direction, vertical acceleration, and that's g cosine of the banking angle in this direction, plus the vertical component of centrifugal acceleration, v squared over r sine of this angle. So here's g cosine theta, and here's v squared over r sine theta. Normally on an unbanked turn, the rider will only weigh 1g. But as a result of banking, there is also acceleration in this direction due to centrifugal. So depending on the banking angle, theta, the velocity of the roller coaster car, v, and the radius of curvature of the turn, the rider may weigh more or less than his normal weight as a result of a banked turn. Okay, so next I'm going to do an example in NoLimits2. And this is an assignment you might want to give to your students. And what I'm going to do is I'm going to build a circular flat track of radius 20 meters. And I'm going to provide a velocity of 60 kilometers per hour to the accelerator. HE's acceleration. That's really not that important. The most important thing here is, as it moves along the circular track, its velocity will be approximately constant. It'll drop a little bit with distance due to friction. And then I'm going to compute the horizontal acceleration. Okay, this is a top-down view of the track that I've created. It's a 20-meter radius track. The acceleration station will accelerate it to about 60 kilometers per hour. By the time it gets to this point here, it's traveling at 57.4 kilometers per hour. So I'm going to compute the horizontal acceleration, and that's equal to v squared over r times 1 over g. So 16.1 squared divided by 20 divided by 9.8 is 1.32. Okay, that's the number of g's. If I click on the g-force cone here, which tells me the number of g's, I get, let's see, 1.3 lateral g's. Okay, I get vertical g's of 1g. Okay, so where did that equation come from? Well, the usual equation for horizontal acceleration is minus g sine of the banking angle plus v squared over r times the cosine of the banking angle. Okay, but the banking angle here is 0. It's not banked at all. Sine of 0 is 0, so that term goes away. Cosine of 0 is 1. There you have it. This is in meters per second squared. We've been working in a number of g's, so there you have it. That's where that equation comes from. So no banking at a speed of 57.4 kilometers per hour, which is about 36 miles per hour or 16.1 meters per second, 1.32 g's. So what does that feel like? So when you drop something, it accelerates at 1 g, 9.8 meters per second squared, or 32 feet per second squared. So after 1 second, if you drop it, the speed is 32 feet per second. That's really fast. Imagine 1.32 g's of force or acceleration slamming you against the side of the car. So it's a very uncomfortable situation. And that's what an unbanked turn looks like. So you saw previously that an unbanked turn resulted in a level of lateral g's or horizontal acceleration of 1.32 g's. That's with a velocity of 16.1 meters per second. So I'm going to show you that we can solve for the banking angle such that those horizontal g's are eliminated. Start with the horizontal acceleration equation, and I'm going to set that to 0. Okay, I'm going to add this to both sides. So now I've got this. And divide both sides by cosine of theta. So now I've got this. Okay, cosine of theta is the same thing as tangent theta. So now I've got g tangent theta is equal to v squared over r. I'm going to divide both sides by g. Okay, and then I end up with this equation. Now I can solve for the banking angle, theta. So previously for the unbanked turn, I computed this value to be 1.32. So v squared over r times 1 over g of 1.32. If I take the tangent inverse of both sides, I get a value of 52.8 degrees. So at a banking angle of 52.8 degrees, the rider will feel no horizontal acceleration along the car. So that's going to be a much more comfortable and far less dangerous ride for the rider of the car. So I think a very useful assignment for students at this point would be to build a 0G curve and a negative G curve in NoLimits2. And I'm going to do that right now. Okay, so this is a segment of track that I built to demonstrate 0G curves and negative G curves. But what is a 0G curve and a negative G curve? Well, I mentioned previously that a acceleration in the vertical direction, also called vertical g's, is equal to v squared over r plus g cosine of an inclination angle, and we're looking for number of g's, we divide that by g, is equal to vertical acceleration. But we want to set it to 0. Okay, so if we multiply both sides by g, we still have 0. And for that to be 0, it means this term must equal this term. Okay, so we know that centrifugal at this point is in this direction. So here's our v squared over r. And then, of course, g is in this direction. Now, NoLimits2 considers this direction negative, up negative, okay? For this example, we just need to shape a curve with a velocity such that this is equal to this, so this is equal to 0. So what I did was, I went ahead and for this lift is going to get the thing to 28 kilometers per hour by the time it gets to the top, and it's accelerating at 0.5 g's. That's tangential acceleration. So let's zoom in here, and we're going to look at speed. And the speed at that point, so we put our cursor on here, and it says the speed at that point is 27.1 kilometers per hour, rounded 27.2 kilometers per hour. Okay, so V equal 27.2 kilometers per hour. Working in meters per second, that gives us 7.6 meters per second. So what I did was I shaped. I pulled these vertices around until I got a curve which gave me 0 vertical g's. And I know it's 0 because there's no spikes here at this point. The spikes indicate the amount of g forces in the vertical and horizontal direction. And again, when I put my cursor here, I'm getting an estimated vertical g of 0, 0.05. Close enough to 0 to be 0. all right? Okay, so that's 0. So what I decided to do is solve for the radius such that this is 0 and see if that radius makes sense. So I'm going to plug the velocity in for here, 7.6 squared divided by the radius, and that's going to be equal to g. The angle here, there's no inclination there, so that's an angle of 0. Cosine of 0 is 1, so that's going to be equal to g. That's 9.8. So I solve for r is going to be equal to 7.6 squared divided by 9.8, and that gives me 5.9 meters. And then I said to myself, does that look like a 5.9 meter radius curve? And so here are 1 meter blocks. So 1, 2, 3, 4, 5, 6. That would be the radius. Let's see, 1, 2, 3, 4, 5, 6. So that would be the center of the circle. Here's the radius, r. And let's see, I think it looks plausible. Okay, I can see that. That's a pretty wide curve. Wow. See, there's where it starts up here. That's a pretty wide curve. So I could see that. That's definitely could be the radius or the circle for that curve. Not a very good circle, but okay. So there you have it. R at 5.9 meters. 5.9. 7.6 squared plus, and they're in opposite directions, right? This is going, centrifugal's up, gravity's down, so it'd be minus the 9.8, does give us 0. Okay, so what does that feel like? Okay, you have a vertical acceleration, or vertical g of 0. Remember I said weight is equal to mg, force of gravity, or m times, in this case, because you have more here at play than just gravity, right? You have the centrifugal. So a vertical is equal to m times 0. You weigh nothing. So if you're in this roller coaster car at this point, you don't weigh anything at all. You're sitting on the scale, it registers 0. Okay, what about a negative g curve? What I did here is I went ahead and created a negative g curve. And what's that telling us? V squared over r plus g, again it's an angle of 0, so just plus g, divided by g, and that's our vertical acceleration, vertical g's. Okay, now what this means is, right, NoLimits2 calls that direction negative. Call it down positive, a little bit opposite to the textbooks, but that's okay. It's kind of arbitrary. That means that this term must be greater than this term, right? For the net acceleration to be upwards, and what is it exactly? Let's put our cursor here. At that point, the estimated g-force is minus 2.58. So 2.58 g's in that direction. So the person in that car is accelerating upwards at 2.58 g's. So what would it be like to ride this roller coaster? Let's ride this segment of track and see what that might feel like. Okay, the next topic I want to cover is conservation of mechanical energy. So what is mechanical energy? Mechanical energy is the sum of gravitational potential energy and kinetic energy. The equation for kinetic energy is 1/2 times the mass times velocity squared of an object. So let's look at the mechanical energy at 2 points, at the top of the track and at the bottom of the track. And I'll use the bottom of the track as a reference point. So the potential energy at this point relative to this point is mass of the roller coaster times g times the distance between this point and this point, the vertical distance. The kinetic energy at this point before it starts moving is 0. The potential energy at the bottom here is 0. And the kinetic energy is 1/2 mv squared. So if mechanical energy is conserved, that no matter where you pick along the track, if you sum its potential energy relative to this point, plus its kinetic energy, it should be the same value. So let's see, is mechanical energy conserved here? These green spikes represent the velocity of the roller coaster at various points along the track. So at the very top, it's approximately 0. There'll be just enough speed here to get it to begin to roll down the track. As it rolls down the track, the potential energy is converted to kinetic energy and the speed increases. With an increase in kinetic energy, you get an increase in speed or velocity. The bottom here, the kinetic energy is at its maximum, but potential energy is at its minimum. It's 0 relative to this point. Then as it makes its way back up the track, the kinetic energy is converted back to potential energy and the velocity drops. And you'll see here that it never quite makes it back to the top. How do I know that? Because the green spikes, which again represents velocity, goes to 0 at about this point. Green, where velocity is 0 at about this point, it'll never make it back to where it started. What does that mean? It means that some of the mechanical energy over here ended up in thermal energy or heat. And that would be the combination of air resistance, so thermal energy lost to air resistance, and thermal energy lost to rolling friction. That's the friction of the wheels against the track. Another clue that mechanical energy was not conserved and some of it ended up in thermal is if I compute the velocity down here, it turns out to be 100 kilometers per hour. And yet in NoLimits2, the indication of velocity down here is 97 kilometers per hour. And NoLimits2 does model thermal energy losses. Now, how did I come up with that 100 kilometers per hour? Well, if mechanical energy is conserved, then the potential energy at the top is equal to the kinetic energy at the bottom. And all I did here was I solved for velocity. So velocity is the square root of 2 times g times this vertical distance. So 2 times g, and the vertical distance is 40 meters. So each block represents 10 meters. 28 meters per second times 3.6 kilometers per hour per meter per second, 100 kilometers per hour. So about 3 kilometers per hour of energy was lost due to this thermal energy loss. So let's take a ride on this slope and see if it makes it back to the top.